Mic test. Mic test. Thank you so much, everyone, for coming to Log 2025 today. I'm super excited to welcome all of you here today. So before we start our opening remarks, let's welcome Nina from ASU to have an introduction about ASU West Valley campus. And we cannot host this in-person conference without their support. So thank you so much.
Thank you. Good morning, everybody. Hi, I'm Nina Pfefferman. I'm the director for the School of Mathematical and Natural Sciences, and we're incredibly excited to welcome you here. Is this? Yeah. Yes. No, there's feedback if I go too close to my face, so I'm holding it right here. Is it not registering? Okay, we're going to overwhelm everybody. Hi. In case you were wondering whether or not you should come awake and involved very early in the morning, the answer is we will overwhelm you with decibels. So, good morning. We're really excited to be hosting this, the first of the in-person Learning on Graphs meetings. So let me tell you a little bit something about our school. So you are, of course, here on the West Valley campus of ASU. ASU thinks of itself as one university in many places. West Valley is in the heart of Maricopa County, one of the largest population density and increased rate populations in the country. And we are very proud of our university charter, which is etched on many of the structures around our campus. And the main focus is on building a university around welcoming and including all learners of all types and serving our community as broadly as we can define that community. And so that very much involves things like our excellent faculty and interdisciplinary programs in the School of Mathematical and Natural Sciences, spanning the range from foundational math and pure mathematics through applied math, statistics, data sciences, biology, chemistry, environmental science, and more. We are a small but excited community of scholars and educators focused on knowledge creation and the translation of that knowledge into both education and application to improve the lives locally, regionally, nationally, and globally. Our faculty span theoretical, computational, and experimental approaches, including lab and field-based measures. So we hope that while you're here, you get to know some of the folks who aren't directly related to the conference and maybe form some new collaborations. We are very proud that Learning on Graphs belongs here as a conference. As I was reading through the program, I was very gratified to see the diversity of talks being given. Graphs, of course, connect all disciplines, both by their application, but also by the abstraction of the logic and how they frame questions. So this aligns beautifully with our strengths at the School of Mathematical and Natural Sciences, with links to many of the things we do. We're also launching an incoming center in pandemic science, which has an entire research focus on graphs and networks. So if you're interested in collaborating in applied graph theory on pandemic science, please come back. And of course, we have a commitment to mathematical innovation with real world impact. This is an exciting and rich program over the next 3 days. There are talks on graph neural networks, deep learning, spectral and combinatorial methods, graph-based optimization and inference. And there are applications across such a diversity of scientific fields, public health, and societal impacts. So I am personally looking forward to bouncing in and out and hearing really cool talks. I've already seen a couple of the really cool posters that have gone up. Personally, I'm excited because my own area of research is adaptive networks. I usually work on the math and network science side instead of on the graph theory and computer science side. I'm looking forward to learning and hearing sort of the parallel progress that's being made that I don't know about, and then getting some of the details on some of the cool results I've seen that I haven't had a chance to read up on deeply yet. So I hope that you will take these 3 days not only as opportunity for collaboration among each other and this wonderful, very exciting conference that we are excited to host, but also for collaboration with our faculty across ASU, not just at West Valley campus, although of course I'm biased and I think math and natural sciences are the best folks, including our own Yushuan, for whom I'm very grateful at co-organizing. Please keep your eyes peeled and maybe peruse some of our faculty web pages and reach out and see whom you might get to know while you're here and enjoy the sun in Arizona in December. So I want to thank, of course, all of the co-organizers, reviewers, volunteers, and authors. Welcome to West Valley, and I hope you have a wonderful Learning on Graphs conference. Thank you so much.
Thank you so much, Nina. Cool. Thank you, Nina, for the opening talks. And let's get started on Learning on Graph conference. My name is He Yu. I'm a PhD student from Stanford, and I'm one of the general chairs to organize LOG 2025 this year, together with Yanbang and Adrian. So just some housekeeping rules. Either you're attending in person or virtual, please join our Slack channel. You can post questions, and we'll be relaying questions to the presenters. And you can also check the full schedule and a lot of more detailed information on our website. We will be maintaining the hybrid format, so all our programs are live streamed on YouTube. Yeah, and again, please use Slack to post questions for both oral presenters, keynotes, tutorials, and including poster present using the corresponding channel. Thank you. Yeah, so just to recap, so this is our fourth Learning on Graph conference, and the idea of having a log in the first place is that we want researchers that work on graph and geometric machine learning to gather together and exchange ideas. We want to make it as truly accessible to all community, and our online participation is still free to attend. And this year we are having the first in-person log conference. And we're still maintaining the local meetups around the world. And we have a focus on reviewer quality. We will be announcing reviewer awards at the end of the last day. So at this current time of reviewing, we all know how important reviewer quality is, and this is something that we keep emphasizing on. So this year, we will have 6 local meetups around the world at Tromsø, New Delhi, Pisa, Gandhinega, Sao Carlos, Paris. So thank you so much to all the organizers for hosting the local meetups. And we will have 4 keynote speakers, Aditi Krishnapriyan, Hagai Moran, Melanie Weber, and Michael Galkin. Please check the schedule to attend the corresponding keynotes. And this year we have 3 amazing PCs, Christopher Morris, who is here today, and Alan Vidasik and Mihai Tuturingu, who will be joining us later today and tomorrow. And thank you so much to all the advisory board throughout our 4 iterations of LOG. And I would like to personally thank our amazing organizing committee, who consists of a group of passionate student researchers and faculty members, and without whom we cannot make LOG possible. And they've been working dedicatedly on sponsorship, reviewing, open reviews, and communications, infrastructures, and many of them are here today. So feel free to reach out and talk to them. And I would like particularly thank Professor Isha, who is an assistant professor at ASU, who brought tremendous help to help us to realize the first in-person log at ASU. And thank you for the amazing staff as well. Oh, and Ishan is hiring PhD students this year working on graph machine learning. So free to reach out. Cool. Now I'll be passing the mic to our PC, Christopher Morris, and he will be talking about the log program this year. Thank you.
All right. So also a warm welcome from my side. Very happy that LOG is happening for the first time as an in-person conference. And I think log is important because graphs are the universal language for many kinds of data out there. For example, social networks, molecules, knowledge graphs, and also, for example, discrete optimization. So we have a lot of diverse data that can be modeled as a graph. And of course, we also want to do machine learning over this kind of data. right? And I think learning on graphs in the last couple of years had many success stories. For example, graph learning is now used in many key technologies, for example, in chip design, in drug screening, fraud detection in finance systems, or recommender systems, right? And also many startups now use graph learning as their key technology, for example, Kumu AI, or relational AI, and also others. So graph learning has a lot of success in the real world. And also major players, for example, Google, SAP, or Meta, use graph learning in their production systems. For example, Google uses GNNs in Google Maps. Right, so that's very exciting. And also in AI for science, graph learning is a major player. For example, there's this very nice 250-page survey, Artificial Intelligence for Science in Quantum, Atomistic, and Continuum System by Zhang et al. So very nice, and very nice references to applications of GNNs in the sciences. So have a look at this. So I tried to play historian last night, and I tried to track down the historical development of graph learning to kind of showcase how far we have already come in the, well, I have to say, in the last almost 60 years. So to best of my knowledge, it all started in the 60s with Morgan, the generation of a unique machine learning description for chemical structures. So that was essentially the first reference I could find where someone tried to map a graph to a vectorial representation, and I guess that counts as a very early graph machine learning application. And then 3 years later, there was this famous paper by Weisweiler-Liemann where they proposed the Weisweiler-Liemann test. And then in the early 70s, there was applications in chemoinformatics. So the first chemical fingerprints appeared. And then also in the 80s, they were systematically tested. And then already in the 90s, there were the first graph neural network approaches. So for example, there was ChemNet, and also this paper, Supervised Neural Networks for the Classification of Structures. I think that was by Sperduti. So the Italians played an early role in the development of graph neural networks. And then in the early 2000s, the extended connectivity fingerprint appeared. So that's a success story for chemoinformatics. And then also kernel approaches became very popular in the early 2000s. So there was a lot of development on graph kernels. For example, this work by Rishi Konda, kernels and regularization on graphs, and also random walk kernels by Thomas Gärtner. And then 2 years later, more graph neural networks appeared. For example, there was this paper by Michele, a new neural network model for the contextual processing of graphs. And also a paper in bioinformatics, chemistry by Merkwied, automatic generation of complementary descriptors with molecular neural graph networks. So these were already graph neural networks that are very similar to the graph neural networks and MPNNs used today. And then in 2009, there was this famous paper, the graph neural network model, that I think also introduced the term GNN for the first time. And also the Weisweiler-Lehmann subtree kernel was published at NeurIPS by Carsten Borgwart's group. And I think it also won the Best Student Award paper at NeurIPS back then. And then around 2015, modern GNNs started to appear. For example, there was this paper, Neural Fingerprints by Duvenard et al., which also at the same time published the same, or the first modern AutoDiff framework, and also used that to implement graph neural networks. And then also spectral GNNs were published. And then I would say around 2017, there was really a boom of MPNN layers and GNN layers being published. For example, GCN by Thomas Kipp was published, GraphSage by Will Hamilton, or Graph Attention Networks by Peter Bilikovic. right? And then around 2019, the connections between the Weisweiler-Lehmann algorithm and MPNNs were established, and also more expressive architectures kept emerging, and also different kinds of mathematics were used to understand the limitations and capabilities of graph neural networks, right? So for example, group equivariant architectures appeared, right? And then this also led to many theoretical works and also many connections to mathematics. Then I would say around 2021, graph transformers appeared, and they kind of were or are now the main competitor for MPNNs and other GNNs. And then I would say since last year, graph foundation models started to emerge, especially for knowledge graphs. And I think our keynote speaker, Michael Galkin, later on will also talk about this. All right, so let me quickly also talk about the theoretical foundations. So as I said, around 2019, the formation of the theoretical foundation started, and it started, besides other things, with the connection of the Weisweiler-Lehmann algorithm and message passing neural networks. Basically led us to understanding that message passing neural networks have strict limitations. And then also for spectral GNNs, tools from signal processing were used to better understand these architectures. And now there's a rich interaction between theoretical computer science and different areas of applied mathematics, obviously graph theory, but also group theory, representation theory, and also function analysis and graphon theory. Right, and there have been already several workshops, for example, at the Simons Institute, at Banff, and at Dagstuhl, that clearly shows that the mathematical sciences and the theory community is very much interested in graph learning. Right, and we essentially started out looking into the expressive power, but now there's also more work on the generalization abilities and optimization in recent years, which I personally think is very important. Right, but there was not only exciting theoretical developments, but also very good developments in terms of benchmarking. So I think one landmark paper here was OGB from Stanford that appeared 5 years ago, and that had a major impact on graph learning and how we evaluate graph learning models. And also just last year, Graphland was published, which offers node property prediction tasks from a wide range of different industrial applications. And I think one of the authors is already here, Ludmila. Just last week, GraphBench was published, which offers many other domains, for example, from circuit design, from chip design, algorithmic reasoning, and weather forecasting. And what I find particularly exciting is that now we have many domain-specific benchmark data sets appearing. For example, there's RelBench from Stanford for relational deep learning, and also recently there was, for example, CosmoBench published, which is a benchmark for cosmology. So I think that's very healthy for the field to have these domain-specific benchmarks appearing. Right, and I think we have these successes, but we also have to make sure that graph learning stays relevant. So now LLMs and large language models are the kind of new kid on the block. And well, I think we have to explore domains where graph learning has a unique leverage. For example, in combinatorial optimization or neural algorithmic reasoning, or especially also in relational databases and knowledge graphs, or also in different domains like power grids. I think there the graph structure is really relevant, and the community should maybe look into those domains. Right, and I think we also have to keep on working to devise meaningful and diverse benchmarks that really have real-world relevance, and we shouldn't just overfit on simple data sets like the famous Zinc data set or so. And on the other hand, I think we also need to build better theoretical foundations that are actually aligned with the needs in practice, right? So I think we should look into things like generalization more, especially size generalization and outer distribution generalization, data augmentation, and things like distribution shift. Right? And we as a diverse community should work together to keep graph learning relevant. Right, so after these philosophical remarks, I want to give some hard statistics. So we had 111 in-person registrations. So I think some people still are missing, and we have around 180 virtual registrations and 2,400 active members on Slack. We had 104 total submissions, 6 NeurIPS track submissions, and we will have 79 poster presentations and 12 oral presentations. We had 306 reviewers and 33 ACs, so thanks a lot for your service. And the acceptance rate was 43% for overall papers, for full papers, and 53% for extended abstract papers. Right, and the average score one needed to get a poster in was 6.5 out of 10, and a little bit higher for oral presentation, namely 7.3. And the average reviewer confidence was around 3.7. Right, and also a lot of the reviews were very long and detailed, as you can see from this bar plot. So we highly appreciate all the hard work that went in from the reviewer side. And on average, the reviewer were also highly rated by AC, so around 80 reviews met the expectations, and around 30 really exceeded the expectations. So I've seen some very, very long reviews where reviewers put a lot of hard work into writing a decent review. So this is really highly appreciated and very important to ensure the quality of the conference. All right, so here you see the overall schedule. So I will finish shortly, and then we will have the first oral presentation. And then afterwards, we will have the first keynote by Aditi. Then we will have a short coffee break, and then a first poster session. Then we will have a lunch break, and then afterwards, we will have the first tutorial on relational deep learning. And then later tonight, we will have the welcome reception, and I hope I will see many of you. Right, and one last thing. So as Hyeyu already said, on the last day, the awards will be announced. So we will have Best Paper Awards, we will have Top AC Awards, and we will also have Best Review Awards. So thank you. Thanks a lot for coming, and I hope you will have a very exciting and interesting conference. Thanks a lot.
Thank you, Christopher, for the opening remarks. I apologize, but the coffee break and the lunch break was swapped. So we will, and the poster session was half an hour. We delayed it by half an hour. So please check the website for the most updated schedule. And sorry for the confusion. Yeah, thank you. And now it's around 9:30, so let's go to our first program, which is the oral presentations. And I'll pass to Yixuan, who will be hosting this session.
Hi, everyone. So welcome again. My name is Yixuan He, and I am the person from ASU who is on the committee. And is very grateful to collaborate with this global, wonderful law committee. And also, I'm very thankful for our School of Mathematical and Natural Sciences, and also ASU, all those support staff to help us bring this event locally to our West Valley campus. So also, I want to remind you that we do have free lunch vouchers that you can use. And when you do the check-in, you can also take your T-shirt and the vouchers. So now let me introduce the first oral presentation. The title is Virtual Nodes Go Temporal. For each presentation, we will have 15 minutes of presentation and then 5 minutes Q&A. You can ask them on Slack, and I will keep an eye on it, or you can ask here in person. So now let's welcome the speaker.
All right, can everyone hear me, I guess? So my name is Sufyan. Thank you first to the organizers for making this hybrid. It's pretty nice to see all of you. So I will be, on behalf of my co-authors, I will be presenting our work today, denoted as Virtual Nodes Go Temporal, which was a collaboration with Yasir Jada, who is now at Imperial, Oleg Smirnov and Lily Char, who are also at King AI Labs, which is part of Microsoft Gaming. So usually when we think about graphs, we think about something called static graph. So it's just a set of nodes which are connected with some edges. The nodes itself can have some features. And the idea is that we are trying to learn another representation or a graph representation that could be useful for some downstream task, like classification or node classification. But we are more interested in the problem of temporal graphs. So imagine that the graph itself is kind of evolving during time. So we have a time axis and there are some kind of events that will happen. For example, there will be a new connection between two nodes, which could, for instance, represent someone buying something new in a certain recommendation system, or it could be, for example, a new friendship in a social network. And we don't really know where does these events happen, and the idea is to predict the next one, for instance. That's one of the kind of classification or downstream that we are interested in. And it can also be, for instance, a new node that will join the graph and will get connected to some of the already existing nodes. One way of doing graph representation learning is based on message passing neural network. And the main idea is that the node representation depends on the neighborhood. So we are just aggregating the information within all the neighborhood, and we are trying to update the node representation that could be useful. And we usually do this in a recursive matter, since the neighborhood's representation also depends on the other neighbors, and we just want to see the k-hop neighbors. But obviously putting this into an infinite will probably lead to something like oversmoothing or oversquashing, which is a little bit problematic, and it has been shown in the literature. In the case of temporal graph, this message passing was adapted, such as we have something like dynamic message passing neural networks. And the main idea here is that the neighborhood itself becomes dependent on the temporal aspects, in which we consider something called the temporal neighborhood. And it's as basic as it is just simply all the nodes that a certain node have interacted with during time. And that creates like a neighborhood. And what we want to do is to aggregate the information within this temporal neighborhood. So we can use any function to aggregate, and then we update the nodes. So once we do that, we usually update also something called the state, which is, or the memory, which is just simply a vector that tracks the evolution of a certain node. And some papers have also suggested that we should use something like temporal projection, which can track something like seasonality or different aspect that is useful in temporal learning. But then the same question that I mentioned before of oversquashing and oversmoothing and everything also transfer to the setting. And what we want to understand is how can we modelize long range dependencies here, because if you just put the number of aggregation to be infinite, we'll have the same problems. So how do we modelize this? Our main hypothesis, or what we want to understand, is that if an event happen in one part of the graph, it should reflect on all the other nodes, such as we are able to predict accurately where the next, let's say, link will happen. So given a certain occurrence of an event at T0 to T1, we just want to see how this affect all the nodes within the graph. So we introduce the concept of information flow, which is just a formalism a mathematical formalism to reflect what I have just said. So given a graph at GT here, and the GT plus 1, we apply our CTDG function or any temporal function, and we just want to compute the distance between the two representations for a node U. And we want to do it for all the graphs, such as we understand what will happen. Based on this, we can have a definition of the graph that is basically mu sigma flowing if only and if this quantity somehow is upper bounded by a certain sigma. Obviously, you want to compute exactly this quantity, but it's kind of hard, or you want to do something like a lower bound, but it's impossible without doing some hypothesis. So for the moment, we are only approach it to our upper bound. But it could be a nice extension if someone can do it to a lower bound, for instance. So the main result of the paper is something like this, in which we consider that the aggregation is done like a GCN. And what we see is that the sigma, or the upper bound, depends on two main elements. Basically, the norm of the weights of the message passing function, and also the walks, or what we call the temporal walks, which is simply the walks applied to the temporal neighborhood. Why is that? Because it's a message passing, so the temporal message passing is just a recursive like information propagation. So in the first step, I only see one, and in the other, I see the second hop, etc. So that's why we have this nice walks. But the main result of the theorem is something like this, is that if an event happen in one part and L, the number of chosen aggregation, is smaller than the distance between the node that we are considering and the nodes where the event happened, then the update of that specific node only depend on temporal projection. So the event didn't really propagate to that part, which is a little bit problematic if you want to modelize long-range dependencies. And similar insights can be obviously observed in the case of attention, in which we use an attention mechanism rather than a GCN to propagate the information within the temporal neighborhood. So we see the same insights. The difference here is that the topology is not dependent on the walks, but the degree here. But it's the same overall message. So virtual nodes can be useful in this setting. If we consider that we have our original graph, we somehow split it into different clusters. Each part of these clusters are connected to our parent virtual nodes, and all the virtual nodes are connected to each other. Then if an event happens at one part, for example, here in the right side, the temporal message passing will propagate it to the direct temporal neighborhood. Then the information will also propagate to the parent nodes, and then it will also propagate to all the other nodes within our graph, which could be, in this case, very useful. So theoretically, if we consider our previous system of information flow, we see actually that if we just augment our function f with some virtual nodes, then all the nodes will have an additional term, which depend on k and m, which are the number of nodes per virtual nodes and the number of virtual nodes. And it simply says that basically if an event happen, the information propagate to the virtual nodes, and so the expected information flow will be higher. Obviously, one here can choose to use k equal to 1, like to use one virtual node. But then the information will have a kind of bottleneck, because one node will somehow take all the information, so it's not that very useful. So one should choose carefully this number. So if we look at the figure F, that's the classical temporal message passing, and we can see that the number of updated nodes, which is in red, is kind of limited. But if you augment with virtual nodes, what will happen is that all the nodes will be updated, and therefore we have much more chances of reflecting the event, which could be useful to predict the next one. And in practice, how does it look? Is that given our original adjacency matrix, we just augment it such as we connect all the virtual nodes together. So it's the right corner part, and basically each part of a node is connected to their corresponding virtual node. So the algorithm looks something like this, is that we get a certain clustering function J, or we call it also an assignment function. So each node will be assigned to a virtual node, we build our augmented adjacency matrix, and we just do the classical propagation that we already have. And obviously the algorithm itself is kind of general, so you can use any appropriate clustering assignment function that you can see fit in your specific setting. But in our implementation, we use something like k-means. So how can we choose this assignment function? We wanted to have two main advantages. First of all, is that it should be fast, and it should be accurate in terms of assigning a node to its specific virtual nodes. And one way of doing it is that there's this nice lemma in the case of k-means is kind of known, but basically if you have a space in which all the nodes are separable, then you only have to compute the difference in terms of the adjacency. So the k-means in this case kind of reflect a good, how can I say, community detection somehow in terms of the graph. So we will have a good assignment of the virtual nodes. And the algorithm is the classical k-means in which we update the centers and everything. So it's, we didn't do much here. So if we look experimentally about what happens is that, at least in terms of information flow, here we see the difference between if we augment or not between the two information flows. So it's the gap, and we can see in the majority of times this information flow quantity will go higher. But again, it's upper bound. That's why we see some small values and some higher values. And what we are interested in is how does this kind of make the experimental results better. And that's the last 3 lines. So we take a TGN, we just augment it with our KTVM, and we are trying to see what will happen in terms of validation and test using the TGB benchmark. And we see that in the majority of times there's improvement. Sometimes the improvement is less. And this is basically based on if you just take the data set and you superpose it with the surprise index, then you will see that in the case, if there's the surprise index to be really high, then we don't really have a big improvement. But this is, in general, a limitation of TGN. And we are only trying to augment this. And obviously, as I said, one should be careful when choosing the number of clusters. In this case, if you consider TGBL wiki, which we know is a kind of bipartite, so it turns out that using the number of clusters to be 2 is kind of interesting. But if you just keep increasing, you don't really have a better generalization. So that's a little bit a bottleneck in the method, is that you have to choose the right parameters, which is a little bit tricky. And obviously here we propose k-means, but there are other possibilities to do that. For example, we compare to just random assignment, which already have some improvement, or something like Louvain. And one should also take into account the time and the complexity. And that's what we see here, in that our KTVN is pretty interesting, at least compared to Louvain in our implementation. So overall, and to conclude, modelizing long-range dependencies with classical TGN is kind of challenging, and maybe virtual nodes can help enhance the information flow, and consequently can help in terms of long-range dependencies. So our paper and code are available in these links, and I think we are presenting in the first session poster, the poster session number 1, and I'm happy to take any questions that you may have. Thank you.
Thank you for the presentation. Is there any questions for in-person audience? Okay, there's actually a question online. So someone asked that how can you distinguish between different times if some nodes appear and disappear? With this, they mean how they can distinguish between different scenarios.
In general, in topograph, in our case, we only consider addition of new edges. We don't consider that a new node is added to the graph. Otherwise, you will have to change the assignment and also the augmented adjacency. It will have an extra line. So in our specific case, we only consider added edges, but it could be extended somehow. Technically, all the theoretical and gain from information flow could also extend to that specific setting, but we don't really consider it here. Not sure if I answered the question.
Thank you. So I see that person is typing. Is there any questions from in-person audience? I think they will have some follow-up.
Okay, cool. Yeah, happy to answer. Thank you very much.
Okay, so the question is, it is if some window of 10 times and the end and beginning are the same. So they ask, what's that? So it is if some window of 10 times and the end and beginning are the same. Oh, okay, I see. I got the meaning. So they're asking if the network, because the network is dynamic, so it's going to update from time to time. So if you have some edges, so if you're not working on node changes, right? So you're only working on edge changes. You may have some edge addition and edge removal.
Yeah.
What if for a window of say 10 seconds, you have the same state for the beginning and for the end, but you have some changes in the middle. How do you deal with that?
Usually, at least in what I know in topographs, there's like these batches, and we only consider in this specific case one batch. But I'm not sure we didn't really do the statistical analysis, so I'm pretty sure that within one batch you can't really find something that's added and deleted. But yeah, so.
Okay, thank you.
Thank you very much.
So our second speaker unfortunately have all their visa rejected, so they're only going to be able to present online. But probably this will be the only Zoom oral presentation throughout the whole conference. Yeah. So now the second oral presentation has the title Efficient Neural Common Neighbor for Temporal Graph Link Prediction. And this will be presented by a group led by Xiaohui Zhang, and they're going to present. Welcome, Xiaohui.
Hello?
We can hear you.
Okay. Hello, everyone. First, thank you for the organizer to hold the hybrid conference. I'm Xiaohui Zhang from Peking University, and I'm on behalf of our team here to present our work, Efficient Neural Common Neighbor for Temporal Graph Link Prediction, or TCN, an efficient and expressive model for link prediction on large-scale temporal graphs. Okay. Temporal graphs are everywhere in social networks, financial transactions, and transportation systems. Many dynamic structures can be represented as temporal graphs. Future link prediction is of great importance as it's helpful to capture and understand the structural dynamics in graph evolution. For example, usually we're willing to discover whether two specific persons will interact with each other in a social network. or how the price of a certain stock could change. However, presenting the link existence here can be one of the core challenges, as it's so hard to precisely capture the dynamic law within the temporal graph. Existing methods primarily fall into two categories. On one hand, we have memory-based methods. Memory-based methods maintain a core component, the memory module that stores memory for each node up to a certain time t. When a new event occurs,
Sorry, Xiaohui, could you speak a little bit louder? It's a little bit hard to hear you clearly. Thank you.
okay. On one hand, we have memory-based methods. Memory-based methods maintain a core component, the memory module that stores memory for each node up to a certain time t. When a new event occurs, the memory of the source and destination nodes is updated with the message produced by the event. Then, in the inference process, we can utilize this memory to compute the temporal node embedding, feed it into a classifier, and get a prediction result. These models are usually very highly efficient, and the node memory can be updated and utilized sequentially, leading to linear time complexity. But this efficiency often comes at the expense of expressiveness. Traditional memory-based methods often focus on pure node-wise memory updates, while overlooking the crucial pairwise relationship between nodes. On the other hand, we have graph-based methods. These methods extract temporal subgraphs around nodes and perform method passing to gather the features within the subgraphs. They can pay more attention to the temporal structure within the subgraph, capturing complex pairwise node patterns. So the graph-based methods are typically more expressive. However, this comes at a relatively high computational cost. The message passing over subgraphs need to be conducted for many times, which will be very expensive. This makes them painfully slow and often infeasible to large-scale datasets in many real-world scenarios. So far, we introduced two prevailing methods in temporal graph representation learning. The memory-based methods are usually efficient but limited, while graph-based ones are more powerful but suffer from high computational complexity. To bridge this gap, we learned from the two advantages and proposed our TNCN temporal neural common neighbor. Our key idea is twofold as follows. First, we adopt the memory-based model as our backbone to maintain the model's efficiency. Upon it, we adapt the powerful pairwise modeling principle of neural common neighbor to the temporal setting. Second, we design an efficient module to extract multi-hop common neighbors using parallel sparse tensor operations, enabling rich pairwise representations of NCN while declining the computational burden. To better understand the effectiveness of our TNC model, we first talk about why it is necessary to capture pairwise information. In other words, how does the pairwise representation works in the temporal graph link prediction task? Here shows a toy example. Figure A shows the failure case of link prediction based on node-wise representation. Such methods cannot distinguish node U and V because we can see in figure B they possess the same temporal computation tree, thus generating the same node representation. However, when we try to learn their pairwise representation, I mean pair U and W and V and W as features, we can observe in figure C, V has a temporal common neighbor B with no W, while U does not have any. With the same computation graph, we only need to utilize the extra node B's embedding to distinguish UW and VW pair. So from this talk example, we can clearly observe that pure node-wise methods fail to distinguish nodes with similar neighborhoods, but different connection patterns. In this case, we should resort to pairwise information such as common neighbor as a better resolution. Now let me walk you through the core of a model. The model has three main components: the memory module, the temporal neural common neighbor module with an efficient CN structure, and an NCN-based prediction head. Here shows the pipeline of our TNCN. It operates through a sequential update and prediction framework, processing successive batches of message. In the upper part of the figure, we can see during the training and update phase, TNCN updates the neighborhood dictionary and node memory. In the lower part, the inference phase, the model retrieves neighbors to identify common neighbors, leveraging the representations of the target nodes and their common neighbors for prediction. Now we separately introduce the three core components. The first one is the memory module. We use a standard memory-based backbone, similar to TGN, to efficiently store and update the node memory over time. This gives us temporal node embeddings without the repeated computation within successive temporal batches. The temporal NCN module is our key innovation. It stores historical interactions in a dynamic lookup dictionary to fastly retrieve the neighbors for each relevant node during subsequent inference. We equip this module with a crucial component called efficient CN extractor. This extractor is designed to extract multi-hop common neighbors for given source and destination pair. We adopt sparse tensor manipulation, which supports batch operations and parallel processing. We first introduce the multi-hop common neighbor. We extend the traditional common neighbor to arbitrary ij hop common neighbor. Here, ij hop represents that the node is in the ith hop neighborhood from the source node and jth hop from the target node. So here, the traditional common neighbor is exactly a one-hop common neighbor. Let's see this example. Here, node 0 and 15 shares 3 1-2 hop common neighbor. Node 10, 11, and 12 in green, and 2 1-hop neighbor. 13 and 14 in red. Besides, we also consider the historical interaction frequency of the source and target nodes, which we also call as serial-hop common neighbors. With extended common neighbor information, the model can perceive the local structure to a large extent and distinguish the difference between multi-hop common neighbors more precisely. When prediction is needed for node pair U and V, the CN extractor conducts an efficient extraction process as follows. In detail, we organize the historical interactions in the sparse tensor format A and B, representing the temporal adjacency matrix for node U and V. Assume that we need the k hop common neighbor, that is, the common neighbors with both k hop away from node U and V. First, we perform self-multiplication to generate high-order adjacency connectivity and take U's up to k hop neighbors and V's neighbors in vector n, 0 to k. Then we employ sparse matrix Harmonic product to calculate multi-hop common neighbors. And finally, we conduct vector subdivision to exactly obtain the kk hop common neighbors. Getting arbitrary ij hop common neighbor also follows this procedure, but will be more sophisticated. With the support of sparse tensor operators by PyTorch, all this procedure can be efficiently implemented and supported by GPUs to facilitate fast and batch processing. After extracting the representation of multi-hop common neighbors, we finally construct our NCN-based representation. For source and destination nodes, we perform an element-wise product. And for multi-hop common neighbor nodes, we aggregate their embeddings in each hop with sampling. These embeddings are then concatenated and fed into the prediction head, such as an MRP, to output the link prediction result. To facilitate the research of temporal graph learning, we also provide a theoretical analysis of several core components within the framework for temporal graph link prediction. We explore two-dimensional capability, the encoding capability, and the efficiency. For the encoding capability, we conclude that memory-based approaches can encode any monotone k-hop events with arbitrary k. Here, monotone k-hop events stands for a sequence of consecutive edges that possesses monotonically increasing timestamps. As these events happen sequentially in time dimension, intuitively, the message contained in the former event can be passed to the latter one, thus aggregated into an endpoint. Look at this example. In this feature, there are 4 nodes. The left shows a monotone event chain for node D, because if we trace back from D, we find the time is monotonically decreasing from C to D at T3, B to C at T2, and A to B at T1. During the sequential message passing, the message from A can first pass to B, and both messages will pass to C and final to D. So D will gather all 4 colors. However, for non-monotone events on the right, D can just collect 3 colors, yellow, blue, and green. because node A is blocked by node B, so the red in A cannot pass to the forward nodes after T1, thus delay the feature capturing processing. As for non-monotone event change, the ability to encode such events is still blurred and is open to survey. For other expressivity, we have 2 points. First, TNCN is strictly more expressive than classic heuristics like common neighbor, resource allocation, and endemic DAR. Second, under comparable conditions, TNCN is strictly more expressive than memory-based models like Joly, Dirac, TJT, and TGN self, because it explicitly incorporates the neural embeddings of common neighbors. For efficiency, we have formalized the time complexity for different approaches. Memory-based methods like TGN have linear time complexity. Here, E is the edge number. In contrast, one-hop subgraph-based methods have a quadratic lower bound and a corresponding upper bound. For two-hop methods, it is even worse with an approximately third-order upper bound. From this toy example, we can also find that memory-based methods takes the minimal computational cost. It needs a total 8 times computation, while graph-based methods takes 9 and 13 times for 1 and 2-hop subgraph method individually. This result formally explains the huge efficiency gap between the two prevailing methods, and it highlights the advantages of memory-based methods, which can mitigate the computational efficiency challenges associated with large-scale Temporal graphs. Now, let's look at the performance of TNCN on large-scale real-world datasets from the Temporal graph benchmark. You can see TNCN achieved the new sort of results on the review dataset. On other large datasets like Wiki, Coin, and Flight, it also shows highly competitive performance, consistently ranking second or third. It can outperform both efficient memory-based models and most of expressive graph-based baselines. To be thorough, we also tested on small and medium datasets. Here, TNCN achieved 6 new sorted out of 7 datasets in transductive setting, and 3 out of 7 datasets in inductive setting. We also conducted an ablation study. It confirms the value of our common neighbor extensions. Moving from just one-hop common neighbors to include 0-hop and 2-hop neighbors provides clear performance gains. The 0-hop neighbor, which represents the node itself, is crucial for capturing historical interaction frequency. And TNCN with 0 to 1-hop common neighbor markedly surpasses the traditional 1-hop common neighbor on various datasets. However, in our experiments, the inclusion of 2-hop common neighbors yields mixed results, as 2-hop common neighbors may introduce more noise to interrupt the prediction. Now let's see the efficiency of this model. Critically, TNCN achieves this performance with outstanding scalability on the real-world datasets. Compared to graph-based models, TNCN achieves training speedups of 2.5 to 5.9 times and inference speedups of 1.8 to over 30 times. It exhibits a comparable order of magnitude in terms of time consumption to memory-based models, validating our design for large-scale applications. Okay, to conclude, we propose TNCN, a model that successfully balances high expressiveness and high efficiency for temporal graph link prediction. The key is the efficient extraction of temporal neural common neighbor with the adoption of a memory-based backbone. TNCN sets new sorted results, offer remarkable scalability, and provides strong theoretical guarantees. Thank you for your attention. We're now happy to take any questions.
Thank you, Xiaohui, for your talk. Is there any question from in-person audience? Okay, I will ask a question. So, you just mentioned in your ablation study that you have much better result for 0 to 1-hop common neighbor inclusion, but the results are mixed for 2-hop neighbors. So, have you done any analysis on the expressive power of incorporating more hops? Is there possible to make use of more hops, take more hops into consideration and still achieve better results?
Thank you for the question. In fact, we didn't take for many hops because when we take 0 to 2 hop common neighbors, the computational cost will increase for some extent, and we find that 2 hop common neighbor yes mixed results. Then we tried the third hop neighbors, but at the same time the result will not be better than 0 to 2 hop, and the computational cost will be larger. So we didn't take the results in the paper.
Okay, thank you. So yeah.
So do you think the architectural advantages that you have will translate to other levels of tasks, like from node task or graph task?
Oh, sorry.
Do you think the advantage that you observe can translate to different node property prediction task or graph property prediction task as well?
Okay, thanks. We think it can be transferred to the node property and a graph property because such common neighbor, a multi-hop common neighbor, will certainly bring about more sophisticated patterns and more information. So I think it will be beneficial to the node properties because the common neighbors, more common neighbors, and such information will help to predict the node state. And for the graph state, if we know some central nodes will share many common neighbors or share less common neighbors, it will also bring benefits to predicting the graph state. Yeah. So I think it is also transferable.
Okay, thank you.
Any other in-person questions? Okay, I will take an online question then. So, is there any theoretical justification for common neighbors compared to other heuristics? Can the method be generalized to other link prediction algorithms originally defined for static graphs?
Okay, thanks. So compared to other heuristics such as RA, AA, we didn't have the existing theoretical justification. Yeah, we didn't compare the results. So it may be discovered later. And for other link prediction algorithms, yeah, for static graphs, we know the temporal graphs can be transferred to a static graph, and although the timestamps, the static graphs have no timestamps, but however, we can use this multi-hop common neighbors to predict link existence for static graphs. And by the way, our multi-hop common neighbor is just the extension upon the neural common neighbor from static graphs. So yeah, I think it can, of course, generalize to link prediction algorithms defined for static graphs. Yeah.
Okay, thank you. Any other in-person questions? Okay, another online. So, do you include a part of the memory where they save periodic information if the period is larger than the memory size?
Okay. Mm, we didn't deliberately save the information time before the time a time window. Yeah. For example, we for want a common neighbor. If we extract the common neighbor, we can set up the lookup dictionary, and the lookup dictionary is restricted to the time window. But for the memory, the known memory can be accumulated from the start of the graph. And so the memory at time t we need to predict is certainly contains the information before, but yeah, we didn't deliberately have a periodical information saved in the memory.
Okay, thank you very much for all the questions and the answers, and thank you, Xiaohui, for giving your talk. And now let's welcome the last talk for this oral presentation.
Okay, thank
Yeah. The title will be Generalized Degrees for Scalable Discrete Time Dynamic Graph Generation. And this work will be presented by Keantan. Let's welcome Keantan on stage.
All right. Thank you, everyone. My name is Keartan van Driel. I'm a PhD student at the Complexity Science Hub in Vienna, and I'll be presenting some work that I did with my collaborators, Leonardo Ialongo, Pablo Esteves, and my supervisor, Stefan Turner. So I won't be going into the title too much right away, but what we'll be doing is we'll be looking at discrete time dynamic graphs. These are generally the result of some kind of administrative data or anything else where you are kind of inevitably coarse graining the graph data that you have. Sorry. All right. Thank you. Does this work? So for our purposes, it can really be quite general. So we have snapshots at each point in time, denoted by integers, and it contains a vertex set, edge set, some node features and edge features. And we are particularly interested in prediction problem. So given some history of graphs, what will the next snapshot look like? Which you can formalize generally quite like this. But here we have to be quite careful. So graph prediction is now quite booming, especially when it comes to material science, molecular generation, and these things. But as is quite known, it's quite easy to overfit here and difficult to really demand some measures of what it exactly means that you want out of your dynamic graph or out of your graph generation task. And so we are a bit more humble and we just demand some specific things. So what do we want? We want it to be scalable because the data that we work with is really rather large. We want it to be in discrete time because the data that we use is a result of this kind of administrative data. And then the thing that this talk will kind of focus on is we wanted to capture local dynamics. And I'll explain in a bit what we exactly mean by this. And quite importantly, that was not supposed to happen. Quite importantly, it needs to be inductive. Dynamic graphs are generally changing over time, and new nodes will be added, some nodes will be removed. And what this generally means is that you cannot take a static node set if you want to do out-of-sample prediction. And so what do I mean with local dynamics? So consider the following, where you have this node F, and it has two different kinds of nodes feeding into it. And this is some kind of functional relationship. Think of some kind of recipe, maybe, to make something. And then over time, by some dynamics, this relationship gets severed. And to continue its operation, this node needs to find a new new neighbor. And this happens. However, this happens within a kind of time window, which is also the discretization of our data. This is some PowerPoint artifact. I had it on Keynote. It happens within some time aggregated window. And what this means is that actually from our perspective, it just looks like at some point in time it had it, then it maybe had both, and then it has the other one. But what's quite notable here is that in these kind of situations, the dynamics are quite constrained. You cannot individually take the links and because the different dynamics between the nodes, they are quite dependent. This is also an artifact that you get with the time aggregation. Now the zoom is in the way, but of course, all kind of normal real-world graphs, they are the result of some kind of aggregation, and so the higher order structure that we see there is a result of this aggregation. And this you get in this intermediate regime of discrete time dynamic graphs. So current paradigm cannot capture this very well because it's mostly focused on link prediction. And when you optimize for link prediction, you are looking for the object. What is the probability that I connects to J at some future time, given the past, usually parameterized by message passing or some other kind of architecture. And this is equivalent to assuming some kind of independence between the links. And so we want to capture such structural dependencies. And so we try to propose something to learn the local node dynamics. So in this talk, I will give a very brief introduction to the framework, then how we implement that in this work, and some of the results. So let's take a look at some local node dynamics where we have this teal node. It has some incoming neighbors and some outgoing neighbors. What we can do is we can kind of flatten this out. And so what you see is that you kind of get these bit strings over time, where it's from t-1, t+1. And then you have some parameter tau that tells you kind of how far you look previous in the past. And if you look at this bit string representation, what you can see is, for instance, we have this bit string that goes 1, 1, and then it gets a 0. And what we can do is, yes. But in this kind of representation, it becomes immediate that the stuff that we saw previous, this kind of dependency, you can capture here. Because here you see that it was there for a time step, then it was there again, and now another node takes over. And so just looking at it like this is able to capture such a dependency. And what we can do is we can count in a vector D, we can count how many of each bit string we have. So we have, in this case, a bunch that's outside of 0, 0, 1 of 0, 1, and 2 of 1, 1. And then we can look how many of each bit string will be completed by a 1. And the kind of, this is inspired by the work of Antonio Longa. And we can kind of generalize this. That looks bad. Okay, that's very poor because I had it on Keynote and there's supposed to be an animation here and it's quite crucial to the talk. So I don't exactly know how to proceed here because this is the essential point of the talk. Is it possible to load it on my computer real quick, or is this not doable?
I feel like you can load on your computer and you share screen on Zoom.
I can also just, yeah, I can just move it with my mouse. It will just be a bit hacky, but I will just move this picture, all right? Okay, so the framework is as follows, where we start with the graph history, and for each pair, I and J, and it's really crucial that you think of this as each pair, even the nodes that are not occupied in between, we give them some kind of embedding. In previous example, this was the bit strings, but it can be the result of pretty much anything, like message passing or some other kind of architecture to embed information in edges. Then what we do is we assign each of those edges a color with with this function pi, which we call the edge partition function. And again, previous, this was just going to give this label, yes, you indeed have this kind of bit string. And then also for incoming and outgoing, but we leave that a little bit outside. Then what we do is for each of the different colors, we count for that node, how many do you have? So in the example here, you see that it has 2 red links. And then to describe the node dynamics, and this is kind of, I guess, the innovation, is we count for each color how many will be active in the next time step. And this is, in a sense, it's kind of neighbor agnostic, because once you've been assigned a color in this framework, it's the same. And so it's quite crucial for applications that you have a meaningful assignment of these colors. And yeah. And so in short, I am now scared to do the actual full screen again. This kind of summarizes the framework and what it allows us to do. It allows us to capture these node dynamics, and quite importantly, the thing that we learn, which is these R vectors of how many will be active in the next time step, they are dense because they are defined for each individual node. And then how we parameterize this or try to learn it based on the graph previous, this is then kind of in the open. And so how we imagine that this framework is used is you have your history, you generate the embeddings, you extract these node degrees, you sample the realization counts for them, however you would like, and then you generate a snapshot. And this is also kind of outside the scope of the specifics. And so our specific implementation is as follows, where indeed we take the example that we've had previous, where we, as scholars, we have the different bit strings. We have them for the incoming nodes and for the outgoing nodes. And then we learn the joint distribution over the realization counts. And the fact that it's a joint distribution gives you that you can get these kind of correlations between the local structure. We learn it in this case, this is some kind of details, but we learn it using a normalizing flow with variational dequantizer, because of course these realization counts, they're discrete, so you need to somehow deal with that. And we make a grand simplification where we don't use some fancy architecture to condition on, but we use the generalized degrees themselves as information. And then there's a very simple way in which, for direct networks, you can generate a graph based on this. Does this work? Lovely, thank you. So first, for each node, we sample these realization counts. That effectively gives us different stubs with different colors. We fix the incoming stubs. So that is really the amount of incoming links that you'll get. And then the outgoing stubs we get by connecting the incoming via some kind of rule. You can stare at it for a while, and then it becomes clear that this approximately gives you the out degrees, but will give you the in degrees for sure of the ones that you sample. Yeah. And so the results with this framework, we have some structural properties which are important to us, which we wanted to capture. And we wanted to ask, is this actually informative beyond looking at individual links? We do this on 2 data sets. One is one that we are particularly interested in. We call it Ecuador. It's a data set of firm-to-firm relationships in the country of Ecuador. It's defined over 9 years. It contains a lot of firms, a lot of edges, which makes this scalability important. And to kind of couple to the literature, we also use the GGBL Fright dataset, particularly because there's been a lot of benchmarking done on it, and it's the largest. So for the structural properties, one thing that we believe every method should at the very least get right is, to some degree, how much overlap out of sample will you get with a reference time point. And so both it was trained before the T is 0, and then we have this wiring rule and we see how much overlap do you have with previous time steps. We also have properties for new nodes. So if a node enters the network, what is the kind of degree structure or structure that it has? And we see that we capture this quite well for the incoming time step, where gamma degree is our method, the proposed is the ones that are sampled, and then the realized is the one after the linking. And you can see that it approximately gets it right. It matters that it's the out degree, because that's the one that's approximate. The in degree, of course, we get right because they are the same. And then it's the exit rate, based on a degree, one of the degrees, what is the rate at which you exit the network. And for the link prediction, we wanted to just simply investigate whether just knowing the temporal structure of an individual link versus the temporal structure of the node, can this framework be a little bit more informative. And so we did that also in TGBL Flight, because then we can compare it to other methods as well. And these are, I believe, the most important results, where this gamma degree is really a derivative of this normalized flow model. It's not then some link prediction model that's sampled. You should read a bit more specifically if you're interested in how we did this. But then compared to FBank, and FBank just takes the bit string of a specific link, and then the frequency by which it's completed by a 1. And you see that for T is 1, that's exactly the same as EdgeBank for 1, and for T is 2 and 3, then you start to slowly outcompete EdgeBank. Of course, then in the literature for TGBL Flight, you have different other kinds of EdgeBanks, and then state-of-the-art link prediction. And what's notable is that we are very close to some of the specifically optimized link prediction, while this method is definitely not optimized for that. And so in conclusion, we introduced a framework that captures local node dynamics, the generation and learning skills approximately in number of nodes. What's next for us? We have done some further benchmarking. If you're interested, please come and find me. And we are now also learning to actually get the link partition itself, so that you can get meaningful classes out of this. And I think this is quite exciting. And we are now actually learning a model that does the linking for us. Thank you.
Thank you for a great talk. Any questions from in-person audience? Okay.
Hi, yeah, so thanks for the interesting work. So I have a question about, so you mentioned that you can capture well the local dynamics, but how do you think a general model can capture more global dynamics, such as how the community evolves, and then how to use that information? So for example, if you have a COVID forecasting problem, so you're going to generate the contact graph of how human changes in the next few days, and you don't actually care about who is connected to whom, but you care more about the overall disease spread or diffusion process over the graph over the next few snapshots. So how do you think about it from a more global point of view? Thanks.
Thank you for the question. I think it's, in my mind, one of the best questions. So there's 3 answers. I'll try to be very quick. The first is that the representation which we build is actually coming out of the kind of the COVID work that was done. And so it's about contact networks, these kind of graphs. So this really much is in that kind of heritage. The second point is that the kind of physics literature that builds on that as well. We are now going more in the machine learning part, but there's some physics literature that builds on this as well. And there they show that you can, with changing the wiring rule that you have specifically, you can retain certain community structure quite well. So that's very, very nice. So we do, and then the third, which is I think most relevant for us, we do circumvent kind of the independent link assumption, but of course the way that we do it now, it's kind of subtle, but we make an independent node assumption as it is right now. And this needs a lot of thinking, especially with the wiring later, on what do you lose, because there are similar results on kind of the limited applicability of the link models. There's also some results that if you do node independent, you still lose some. And so maybe in the linking or some kind of correlation needs to be introduced or dependencies between the nodes as well. I'm thinking about that. So if you want to talk about it, please.
Thank you. Any other? Yeah.
How is the link coloring happening? Look at the end. You said you're starting to work on like learning those, but at the moment,
yeah. So this is for me has been the hardest point to get across with this work is what we are and what we are not doing. So we learn this R as it is now, which is given this coloring, and how we're coloring it right now is we are coloring the links based on their past activity. So right now you see that, let's say you were active at t minus 1 and you are active at times t, then you have a bit string 1, 1. That is your color. And then the direction also matters. And now we are actually also learning this. So, but that's not part of this yet.
Thank you very much. I feel like it's already 10:30, so I will not occupy the next session. Thank you, Kanta, again for his great talk and also the great question. So the next session will be a keynote speech, which will be introduced by He Yu.
Yes. We need 5 minutes to set up. So our first keynote speaker will be Professor D.T. Krishna Priyan, who is an assistant professor of chemical and biomedical engineering and EECS at UC Berkeley. And her research interests lie in developing methods in machine learning that are driven by the distinct challenges and opportunities in natural sciences, with particular interest in physics-inspired machine learning methods. So let's give her a round of applause. Oh, and you can post questions in the keynote discussions channel if you are a virtual participant.
Great, thanks for the invitation, and it's good to be here. I feel like some parts of this talk, it might be a little bit controversial given some of the trends that I've seen in the field over the years. And so this is really going to be trying to frame this as this is a field of ML for science that has looked at graphs quite a bit. Is this something we should be thinking about going forward for what the right modeling paradigm is? And my background and my training is originally in the sciences and in mathematics, and I'm now in 2 engineering departments, and so that's also starting to shift some of my views about where should we go for the most impact, the most practicality. And this is work with a lot of the great students that I get to work with at UC Berkeley. So I'll start by just giving a general introduction of AI for the physical sciences. I think this is a field that has gotten quite popular in the last few decades. There's a lot more interest in trying to come up with ways that machine learning can be used for real scientific impact. And then I'll also talk next about some of the shifts in the direction of this field, which I think has mirrored a lot of other fields of machine learning. And that'll really be a springboard to some case studies that we've started thinking a lot about in terms of the graph structure, in terms of symmetries, and to what extent we do need to build these into our machine learning models. So this is going to be maybe the slightly more controversial or discussion point topic. And then I'll also just briefly talk about looking at the future. Should we also be going beyond pure ML modeling approaches? Are there ways that we can actually leverage these models for downstream tasks and go beyond just the model building in and of itself? So I'll start with some background on AI for the physical sciences. I'm not fully sure what the full scope of background is, so I'll just give some motivation about why this is what I think a very exciting area. So the physical sciences, this describes our whole world from atoms to fluids. And if we could model spatial and temporal behavior in these scientific systems across all of these scales, we could really unlock some huge advances across the sciences, ranging from renewable energy, drug discovery and medicine, modeling the atmosphere better. There's really a lot of room for impact if we could come up with better ways to model these systems at really large system sizes, very long timescales. And the reason we care about this is because many interesting things happen at long length and timescales. So for example, a protein folding, a lot of the really useful aspects come from if we can really blow this up, really understand how this behaves over time to understand what the functionality of these systems will be. And this is really the overview of a lot of the research that we do, where we're trying to understand how to enhance and advance this physical modeling through machine learning. So we could start with things that are at a quantum mechanical level, so things at very small scales, very small time steps, and we try to build these unified models to go up to molecules, to coarse-grained representations, all the way up to fluids. And if we could come up with a general way to describe all of these systems, this would be really transformative across many, many different scientific applications. So this is just so fundamental that it would affect many, many different things. And historically, graphs have been really popular in AI for the physical sciences. So molecules, you can represent them as a graph. So for example, the atoms could be nodes. You could come up with some radius cutoff of a receptive field and treat those as edges. You could also represent all sorts of atoms. So materials can also be represented as graphs, proteins as well. You could also represent these learned fluid dynamic simulators as graphs and essentially do large-scale particle modeling. So this has been a very popular approach in the field for a long time. And I'll use a lot of this case study that I'm going to talk about here. I'll use statistical mechanics and molecular dynamics as my motivating use case. I think some of these principles are relevant to many different application areas, but I think often to develop methods, you need to keep at least some application in mind to figure out how to stress test it, figure out where you can improve it. And I think molecular dynamics and atomistic systems is a really, really fundamental type of science, because if we could model the atoms in the world, we could essentially model everything around us. And these atomistic systems, they exist in an ensemble of states described by some potential energy surface. So you have these atoms here, you have some complex potential energy surface, and this is something that typically follows a Boltzmann distribution. So the probability distribution of this follows this Boltzmann-like distribution where we have this dependency on the energy. And if you can figure out how to sample from this potential energy surface, you can essentially do all sorts of downstream tasks. So you could, if you could sample accurately, you can do molecular dynamics, so you can compute the dynamics of these systems. You could compute the geometries of these systems. You could do some type of free energy calculation. So if you have a protein and you have a molecule, what is the lowest energy state to appear in the real world? All of those can be done from really good sampling from this potential energy surface. So the fundamental problem here is, how do we learn or sample from these high-dimensional Boltzmann distributions? And this is quite complicated because as your system gets larger and larger, your problem becomes very, very high-dimensional. And there's a few different ways that you can do this type of sampling. This is essentially following Langevin dynamics, so very similar to the underlying principles of generative models, where you could have some atomistic structure, you have a function to estimate the potential energy. you can differentiate it to get the forces, and then you can go ahead and time integrate this whole system. And this is what we would call some type of force field, where you learn the forces and you integrate over time. And sampling is really hard, so there's lots of room for improvement here. One thing is that estimating that potential energy surface is very, very slow, so you could do it through experiment. This would take a really long time to measure in a lab. You could also do it through very high fidelity quantum mechanical simulations, also very expensive in general. And the other point is that it's possible that you might want to see something at a very long time scale, but you're taking very, very short time steps. So it could take millions or billions of time steps to actually see what you want. So because of this really fundamental difference in where we need to be to do new science versus where we are now with current methods, I think machine learning has really taken off in this field because it's a very nice place and alternative to use machine learning as some surrogate model. Maybe we can do some really new impactful science by solving problems like this. And there's a few different types of ML options that you could go over to solve this type of problem. One option is that instead of using some expensive method to get the potential energy, you use machine learning as a surrogate model. And this can typically be done by if you have a data set where you're learning some structures and you have some mapping to energies or the forces of the system. You learn some model over that, and then you can just quickly query that model at this stage over here rather than running something very slow. The other place this also comes up, and I think there's a lot of very elegant problems that you could do within the context of generative modeling here. And one approach here is that you could directly sample from the underlying Boltzmann distribution. So our goal is that we have some data set of samples from our Boltzmann distribution, and we learn a generative model to actually map that random noise to the data sample. So given some random noise, we can generate some new structure with that. And our goal is to adjust the model parameters so that the samples are getting as close as possible to the real distribution. And this totally skips approximating the potential energy surface along the way. So these are a couple of different paradigms that you could use to try to model these systems better. And now this is the Learning on Graphs conference. And so one of the things that has been really big in this field is the dominant architecture has really been to represent these systems as graphs. So you could represent proteins, molecules, materials as some type of graph structure. And so you could do this with a graph neural network. Often you have many features, like you put in angles, you put in other types of inductive biases into your model. And so each node represents an atom, and then you have some way to represent the interactions between these atoms. And another really popular approach in this field, a place where I think this idea of symmetry-constrained networks has really taken off, is some of these systems, like molecules, for example, obey things like rotational equivariance. So this is equivariance with respect to the SO3 group. So if you make a force prediction out of a molecule, that is a property in a symmetry that is inherent to the system. And so because of that, there has also been a lot of interest in trying to build rotational equivariance or other types of symmetries into these graph neural networks. And this is also a very rich field over the last many years. And just to expand a little bit on these rotationally equivariant graph neural networks, the general idea is you have a GNN and the node features are equivariant to rotation. So if you have a molecule here and you predict its forces and you rotate it, that should be the same as if you rotate the molecule and then predict the forces. And typically, the way that you will do this is to interact certain features, in this case, the basis set of your system. And the energies of the system that you're dealing with, those are invariant to rotations, and the forces are equivariant to rotations. So this is just inherently built into all of these systems. Now, spherical harmonics make a lot of sense as being your basis set and the features that you use to interact different properties as you update, for example, your graph neural network during each message passing update. And it's because they're the basis for SO3, the rotational group. And so there's a lot of really nice intuitive physics that comes from formulating the problem this way. The one thing is that to put and build that rotational equivariance hard constraint into your neural network, this has to typically be done through very expensive tensor product operations because you're essentially trying to interact these different vectors or higher order tensor matrices through some type of operation. In this case, the tensor product is the most natural one. And so at each update step of your graph neural network, you're interacting these very expensive features. And that doesn't scale super well, so it typically is around O of L to the fifth. And so what that means is that as you go to these higher order features, it takes a long time to actually train and actually use your neural network as well. And this was something that the formulation seems very elegant. And so this was something that we also looked at to see, well, could we actually develop more efficient ways to enforce rotational equivariance in these neural networks? Like there's some really nice physics that you can derive. You can show some very nice relationships in quantum mechanics to show these equivalencies of how physics builds into machine learning and neural networks. And one approach that we took to this was something called a Gantt tensor product, where we came up with a much faster way to do these expensive equivariant operations in these neural networks. And at first, this seemed really nice, like, okay, equivariant graph neural networks, they're expensive, but maybe we can still use them in some way because we can just make them faster. But a lot of the takeaways I ended up taking from that are that these equivariant GNNs, they start to saturate in accuracy, especially as you go towards larger data sets. You get less predictable improvements with more data. I think it's going to be hard to win the current hardware and optimization race with what we're seeing with other architectures. And so this really was a bit of a mindset shift for me to think about being open-minded about other modeling choices. So I think graph structure is really nice, symmetry is really nice, but perhaps we should also be thinking beyond this, because if we really want to build the best models for new science and scientific discovery, should we try other options as well and not just stay in this fully specific, more narrow space? And so I'll use that as a chance to also now back up a little bit and just talk about shifts in the general direction of ML for science and how this is really mirroring the shifts of a lot of other fields of ML. And I wanted to give that background a bit so you don't really think of me as a scale is all you need type of person. I really think that that's a simplistic view. But at the same time, I do think that there are certain trends that we really can't ignore in other fields of machine learning. And a common trend that we've seen in other fields of ML is that as you get more data and as you make your models bigger and you have these very compute efficient methods, this tends to lead to better performance. So your model performance really improves as a function of data, computational resources, the model size, and so on. And this is just to say that methods that seem to leverage this data and this compute seem to generally be the methods that are doing the best right now across language, across math, across structural biology, and many different problems. And some very similar trends have started happening now in all sorts of fields. And one of those has been in this area of ML for scientific modeling or atomistic simulation. So in the last few years, a bunch of very large-scale data sets have been developed. These are all based on quantum mechanical simulations, but they're highly accurate quantum mechanical simulations. So it's getting us at least towards a pretty good initial guess and a starting point for using these models to do something scientific. And so we have data sets like Open Molecules, which came out earlier this year, has over 100 million data samples. There's other data sets like Open Materials, also millions and millions of samples. And what that means is that at least with this modality of data, we're not really in the low data regime anymore. And so what does that actually change about how we should think about the problem, how we should go forward with the methods that we try? And the recent shifts that we've seen in the direction of this field now, it starts to mirror other fields of ML, where you had these small, often highly constrained, physics-constrained models trained from scratch each time on small data and new systems. And then we went towards these large-scale, more general-purpose models, these so-called foundation models trained on large data sets. And I think a critical thing that we as a community have to think about now is how do the model design choices change? because many ML methods that are effective with small data sets aren't always as expressive enough to capture all the information across large data. And so when we're using these graph neural networks or these symmetry constrained neural networks, and we could use them with very small amounts of data, suddenly things have shifted a lot and perhaps we're solving a different problem now. And the last point I just want to mention also is that going beyond the models themselves, how can we actually use the initial representations of these large scale models to really push the speed and the accuracy barrier? And in the case of scientific problems, I think there's a lot of problems to work on here. So for example, how do you actually unlock these models so that the scientists, the chemists, and the physicists can easily and efficiently run these models without as many resources? How can you really push the length and timescales to get to experiment in a lab? How can you make sure these are all physically realistic and also in some cases specialize eventually to different systems that you care about? And atomistic modeling in particular, I think it has a lot of really interesting machine learning problems to answer along the way towards getting this new science. So this grand challenge of how do you model long timescales, realistic system sizes. There's also this idea that whatever we do needs to be physically consistent. But there's a number of additional questions that come up along the way. So I think one question that is an important one to explore in this field is some physics easy to learn from the data or harder to learn from the data? And this comes back to this question of should we build it into the model or should we learn it from data? And this is something that I had seen when looking at physics-informed neural networks, which is this idea that when you train a neural network, you try to embed some type of conservation law or physics into the training procedure. And in theory, this comes back to the same point of it makes inherent sense to put physics in the model. But in practice, what we found was that there's a lot of machine learning optimization and training challenges with this approach. And it can be difficult to get these models to converge. There's also the speed factor. It is a little slower to train these models. And so that does bring this point of how do you manage the speed of the model versus making sure things are physically consistent. One big point going forward, I think, will also be bridging the gap between simulation and actually realizing something in the lab. And the last point is this idea that perhaps we should also shift a little bit from our modeling mindset. Tons and tons of models have been built in this field, like many of them graph neural networks, many of them some flavor of equivariant graph neural networks. Perhaps we should be thinking about how to leverage the model's representation themselves and actually use it downstream for something. And we've also seen these trends in other fields of ML that we really can't ignore now, that if we make these models more flexible, so we actually make it less constrained, and we make it, we push the limits of having the expressivity to learn from the data, these models can learn really, really well. And one of the classic examples of this is looking now at the transformer architecture, which is going to have fewer inductive biases than an equivariant GNN. But it turns out that in many fields, even fields that have strict physics, certain types of physics can be learned exactly from the data, and you can actually use these models pretty well for many of the downstream tasks here, ranging from robotics to proteins to weather modeling. So all of this motivated us to do a little bit of soul searching to really understand how should we be thinking about the field going forward. And so we did a number of systematic studies to really try to understand what can more unconstrained ML models learn directly from scientific data, and to what extent can we actually explore this side of this? How should we potentially be thinking as a field going forward based on some of the systematic studies that we might see here? And our initial study, we used something called the Open Catalyst dataset. This was a dataset that was generated by Meta, and it was the largest atomistic dataset at the time. So you have a bunch of different surfaces with atoms. You have a molecule on top of that. And this is around over 100 million different configurations. And the impact of this is that if you have good catalysts, you can convert carbon dioxide to natural gas and potentially help with some of the renewable energy challenges that we're facing right now. And the goal of this would be that given some structure, you're trying to predict something about the energetics or the forces of this system from which you can do all of the downstream tasks. And one of the things that we initially did was an ablation study where we tried to look at what happens if you scale model parameters in different ways. And so what's going on here is that you have these different architectures. So you have an architecture that has, in this case, L equals 2 gives you some degree of rotational equivariance. L equals 6 gives you a higher degree of rotational equivariance. And so when you go from L equals 2 to L equals 6, one of the reasons that the equivariant models are doing better is that they're adding many, many more parameters. And so on the y-axis, we have error, and so lower is better. As you add many more parameters, the models get better. But that's not the only way that you can add parameters. You can also add parameters through the attention mechanisms and make the models more efficient this way. And it turns out that if you actually add parameters through the attention mechanisms, so these are all the things on the right-hand side, you get very similar results. So you get much lower error. In some cases, lower error than the equivariant models, though I think that's with a little bit of an asterisk since they're all within the same range, and this is just one metric that we use to assess the models. But the models are also just much faster. And so if you normalize for the parameter count, these models that don't build in explicit equivariance are doing quite well, and they seem to be learning a decent amount, and they're just also much faster to run. And this initially motivated us to think more about model design choices that scale well and learn expressivity through scaling. And so we stayed with the bounds of graph neural networks and learning on graphs still here. This time we added an attention mechanism. So we created this model, we call it ESCAPE because it's efficiently scaled attention and it's approximating a potential energy. And we came up with this graph attention block, which lets you operate over the neighborhoods of your system rather than nodes. And the motivation for this was that if you construct attention this way, we can scale it more efficiently, and it's much more highly optimized for GPUs as you go forward. So we're still operating in the bounds of a graph, but we've changed a lot of things. We've dropped rotational equivariance explicitly from the graph to try to speed up things more that way. And we saw some nice results with this type of approach. So one thing here was on the x-axis, this is the speed. So if you want to go more to the right, that's going to be faster. And the y-axis, this is the accuracy. And so lower is better. And so you see these predictable improvements that you take this model, you make it larger, you make it even larger. The model does get slower, but it is lowering error. And you see the same trends with the forces. So even though this model doesn't have any type of equivariance built in, it's still doing quite well at force predictions. And in the process of this, we did a lot of systematic checks to really try to understand what these models are learning from the data. And one way you can explicitly check if you've learned rotational equivariance from the data is you take some type of structure and you predict the forces. You then rotate the structure and you also predict the forces. And if you come back to that first structure and you rotate it again, if you've done this correctly and you've learned equivariance, these two output forces should be exactly the same. And when we compute a cosine similarity between the forces on all the test sets, we found that this was exactly the same as models that try to build in equivariance into the models. So it seems like this is actually something that you can learn from the data. And there was actually a nice study that came out recently. This is from Max, who is in Kyunghyun Cho's group at Prescient Design. And so Prescient Design works a lot on molecules, drug discovery, machine learning within that context. And they did a study where they tried to see how quickly equivariance could be learned with these different models. And they used the ESCAPE model in this case. And this is just taken directly from their paper where they found that you could actually learn equivariance almost exactly at only about 25% of an epoch. So this is training steps. This is how well you learn equivariance. And over here, you're already almost exactly at 0. So it's learning it very, very quickly from the data. And this poses some questions about coming back to what's easy to learn from the data versus what's more difficult to learn. perhaps these types of symmetries are not that difficult to learn from the data. So we first had looked at, okay, what happens if you still have a GNN with attention but no equivariance? But now we took it one step further because we do have some larger data sets. And this is where we started to question even the necessity of the graph in and of itself. And so we did this additional case study where we looked at, can these unmodified transformers discover emergent features that are currently hard-coded in the equivariant graph neural networks? And so in this case, we tried to learn directly from raw Cartesian coordinates. So there's no graph at all now. And so this is where I think things get a little bit spicy in terms of what do we actually learn? Is this actually a reasonable learning paradigm for these types of problems? And this is work with Toby and Yutong. So Toby comes from more of a physics background. Yutong is trained purely in computer vision. And I think this also shows that this is, as people from different backgrounds start to work together, this is really going to enable a lot of new discoveries because we get a lot of different perspectives going on. So we did this study on the Open Molecules 2025 data set, and we specifically tried to look at the predictions of energies and forces of these systems. This is just a first approximation. And what we found was that a fully unconstrained transformer learning directly from the raw Cartesian coordinates, it matches the performance of a top performing equivariant GNN. So this is the ECEN model, which was developed by Meta. And I don't want to claim that this is ready for prime time, but this is really a starting point for probing what representations are actually emerging from this learned ML model. And one point to really think about, I think, as a field is this hardware race. So a 1 billion parameter transformer trains and runs inference faster than a 6 million parameter equivariant GNN. And this is probably something that's only going to grow as more and more GPU optimization is specifically made for architectures like transformers versus what might be going on with graph neural networks, just in terms of community size and the amount of money that's being poured into both of these fields. And this is also just something to really think about going forward, the challenges of graph neural networks in scientific modeling. So one thing is that you have to predefine a graph for each new system and do a graph construction. And this adds a pretty high overhead. And you can also overfit to graphs seen during training. So if you have some graph and it has some effective radius cutoff, you can really overfit to graphs specific to what was in your training data. You can kind of see that by if you plot the Laplacian eigenvalues, most of them center around 1. So this is like a diagnostic tool to see that. And so that does mean that you have to be very careful about how you train and use the GNNs. It's also the case that if you're doing edge computations, so if you have features with your edges, which you tend to do with molecules, this does add an expense overhead. It also means you might need to write custom CUDA kernels versus with architectures like transformers. You can go ahead and directly use many of the optimization tools that have already been developed for that field. And if you look at rotationally equivariant GNNs, so this is another model that we looked at from Meta, it's about 270 flops per parameter per atom, and the transformer is about 6 flops per parameter per atom. So this is really the big difference in why you can train such a big transformer, like 1 billion parameters, and it's faster than, say, like a 6 million parameter equivariant GNN. Just a huge difference in terms of efficiency of these models. The other thing that we found interesting was, well, these models, transformers might be more efficient, but what are they actually learning? Are they learning useful physics from the data? And what we ended up finding is that these pure transformers are actually learning the molecular structure without having these explicit hard-coded physical priors. So one thing that we did was we plotted the attention scores of the transformer, and we found that in the first 9 layers or so, attention decays inversely with molecular interatomic distance. In the later layers, attention decays around constant with distance. And what that means is that it seems to learn some type of local feature extraction corresponding to learning something around the forces, and then a global aggregation corresponding to something learning around the energies. And so this is actually very physically sound in terms of what's being learned. This is exactly how we would think about quantum mechanics as a whole to look at these atomistic structures. The other thing is that these transformers are actually learning an adaptive radius cutoff. So they're learning how to adapt the radius cutoff for different molecular sizes, different systems. Whereas a GNN is going to have a fixed graph construction algorithm. So you have a fixed construction, you can do message passing to go further out, but you are losing some information by having that fixed receptive field, especially for big molecules where it might be the case that atoms are interacting outside that receptive field. And so the transformer is actually learning an adaptive radius cutoff as the molecular topologies change. And it's able to flexibly adapt across many new different systems. The other point I also want to make is that these transformers are giving us really predictable scaling laws. So the idea of scaling laws is generally that if you have models that show predictable gains with parameters and with the compute resources, this means that you could potentially forecast ahead of time how big a model or how much data you need to get the performance that you would like. And one thing that we saw in this case is that training a transformer on this molecular data, it's not saturated and the model keeps improving at the same rate with more parameters. Whereas the current graph neural networks in this field do start to diminish in the returns that you get at a much lower parameter count. So they don't predictably get better and better. And I think this is going to be really crucial to think about for a world with more efficient compute and more data, this nice predictability that we get these non-saturating gains as we update things about the model size or the data or so on. One other point I also want to make is that these more unified ML model design choices mean that we can potentially model across different modalities. So this is an example of looking at the 3D Navier-Stokes equations, which describe a lot of fluid flow and fluid dynamics. And one thing we found here, so on one side, this is explicitly a direct numerical simulation. And on the other side, this is an ML model that we developed that's around 30 times faster than this direct numerical simulation. And if you actually model this over time, and this is the ML prediction over time, it's tracking pretty well with learning all of the conservation laws that make this simulation physically sound. Now, this is actually based a lot on many of the same principles that we figured out in the case of atomistic modeling, this idea of going towards more standardized architectures. And so what this means is that as we move towards a more standardized format of data and architecture, these similar ideas can be extended to different types of problems. So we could do this with atoms, we can do this with fluids, and generalize to larger mesh sizes. And this is harder to do currently with the current paradigm of using graph neural networks. So the very last thing I'll mention is also, and this is also really keeping in mind how should we be thinking about the future of the field, where are the problems that we should be working on. I will mention that I think some of the places that there's a lot of problems left to think about are going beyond the models themselves. So how do we build methods that build on the learned representation of these large ML models? And how can we really push this now to unlock new lengths and timescales? And one possible topic here is this idea of knowledge distillation. And this is something that could be architecture agnostic. So it's possible that there may still be ways that we can use graph neural networks here compared to what we're also seeing with other architectures like the transformer. And the motivation behind this is that the recent direction of the field, just like every other field of machine learning, has gone towards these so-called foundation models. So instead of training on individual systems, you train on millions of diverse atomistic structures. You create this general purpose, really large-scale model to be accurate on many, many different systems. But as you make these models larger and larger, you do run into speed challenges. So if you want to simulate for billions of time steps, this is still going to be quite slow to use a so-called large foundation model in this way. And there's another consideration of specialization if we try to think about or forecast what the domain scientists would want. Because even if you've trained on all of chemical space, a scientist might only care about a small subset of chemical space that they want to study. And so a fast model specialized to this area of study might be better than having this slow, more general purpose model. And so this really brings up a question of how do we leverage the large scale models, but still get the speed that we want at inference time, or the physical consistency that we want at inference time. And so this means how do we improve the efficiency of these models, but still preserve the powerful general purpose representation that the large models learned. And a very natural idea here is knowledge distillation. So if you have some large model, a teacher model, you try to transfer knowledge into a student model, to a smaller, more efficient model. And the motivation here is that the small model trained via distillation from the larger model should be better than the small model if you trained it from scratch on just small data sets. And so we looked at this within the context of this atomistic modeling approach. This was a case where there was a lot of attention focused on the large model, or focused on the underlying model and the architecture. But I think knowledge distillation at the time was relatively unexplored. And we also wanted to make this architecture agnostic. So the models are changing so quickly. Can you swap in and out whatever model you want? And so in this case, you could train a very large model that's seen lots of different systems. You do some distillation procedure. We do this based on the Hessians of the energy function. So this is totally architecture agnostic. And you get these specialized fast models. And these are the models that you run for all of your downstream applications. And I think this is still an open area of exploration in terms of what model should you use for the large model, what model should you use for the distilled model. And it's possible that in the distilled case, because you're dealing with a smaller data regime, it might still be useful to think about graph neural networks or equivariant neural networks in this case. I think this hasn't really been systematically studied in terms of the model choices for your teacher model or your student model. I think that could be worth looking at to really try to understand how do we systematically do this distillation better. And what we saw was really this idea of distillation improves the Pareto front of accuracy and speed for different classes of molecules. So this is an example where the large molecule, or the large model is right over here. So that's the purple or the pink dot. And what we want on the x-axis is simulation speed. So more like faster speed is better. On the y-axis, we have error. So lower error is better. And if you take a model that's undistilled, it's fast, but it has pretty high error. Whereas if you take a model that's distilled, it's both fast and it has much lower error. So we get into this nice regime where we're really improving the speed and the accuracy of these systems. And in all of the use cases that we've looked at, typically the teacher model and the student model are different. And so I think that is an area of exploration to see what makes the most sense in terms of the model choice for both of those systems. The last thing I'll mention in terms of this idea of going beyond models is to think about sampling with generative models and statistical physics. And I'll mention this because I think a lot of us really like the elegance of math or physics within the context of could it be useful for machine learning. And it is something to think about that there are cases where maybe the most elegant or the most mathematically elegant option is not the one that ends up being the thing that wins out for more practical purposes. But I just want to mention the area of generative modeling as one example where I think there's a lot of really nice ways you can still utilize certain mathematical formulations to sample better from these systems. And this is again going beyond the idea of models where we start with some large pre-trained model and come up with a way to do some sampling from it better. And the canonical problem that we're trying to solve here is to try to capture rare events that occur over long timescales. So this is something called transition path sampling, where you have these rare molecular events, say like a protein folding. You would like to figure out what's the pathway for that protein to fold a certain way, or the mechanistic pathways. And this is such a high energy barrier that doing any type of explicit molecular dynamics is too slow. It's often also too slow to do that approach where you have a machine learning potential, you predict the energy, and then you integrate it for many, many time steps. And so the goal is, can you directly sample all of these nice pathways in a much faster way? And the way that the field has typically done it now is that it can be slow for each new molecular system because you take some system and you have a separate expensive calculation, or you train a new machine learning model. You go to the next system, you also have a slow separate calculation, and you keep going that way. So you're doing this separate expensive procedure, and you can't really reuse information between all of your different systems. And I think this is another case where we can think about how to leverage large-scale models for something downstream. And so one way that we could think about this paradigm is that we train on some systems using these IID samples. We learn some general representation, and then we quickly predict the transition paths directly without retraining. And some of the key questions we need to answer are how to generate these transition paths initially, and how to make sure that they're physically consistent so we don't have atoms colliding with each other. One way you can do this is utilizing principles from statistical physics. So this is the idea of least actions principles. And there's a stochastic analog for stochastic differential equations, like with Langevin dynamics, called the Onsager-Maklub action functional. And so the idea is that you can take some pre-trained generative model, you can sample from it explicitly using this action minimization approach, and then you can go ahead and use that to predict these transition paths. And predicting these paths is going to be much, much faster than trying to do some type of numerical simulation approach or other types of ML approaches where you're directly predicting the potential energy surface. So the general formulation of this is that you can pre-train a large generative model. You can use the fact that generative models introduce a very natural stochastic dynamics, and that natural stochastic dynamics means that you can use the score function of your generative model within the context of doing some type of action minimization. So minimizing the action function is the same as maximizing the probability of your data. So this is basically telling you that by doing this minimization, we're trying to find the highest likelihood interpolation pathways on the data manifold. And what that gives you is if you have some structure A and structure B, this is a way to find all of those paths within that and it gives you dynamical information explicitly. You can show this on many different types of systems. So a natural place to show this is with proteins, where you have these conformational changes over time. And this is from a very famous data set from D.E. Shaw. And what this gives you is if you apply this action minimization on top of a pre-trained generative model, you get all of these different sample transition paths. You get an ensemble of different paths that could be possible. And this is giving you a very fast, quick prediction to what the dynamics of these systems look like. So I'll go ahead and wrap up on that note with really this question of thinking about ML for science, and also more broadly just framing this as thinking about what is the biggest impact that we could do in this field. And I think that does require some rethinking of how the field has done things in the past, because we are in a regime with more data, more computing resources. And so how do we build upon that? And does that mean that with more data, we're solving a different problem than what we had before in data-starved regimes? And I think something really to think about here is the graph structure always going to be the best choice for this problem? Should we be, in some cases, thinking away from that, in other cases, thinking about other options to come up with the way to represent our problem? I do think that with building these ML models with more data, we should be open-minded about the best model design choices to learn from all modalities of data. It can be very tempting to think about doing one approach because it just makes physical sense or theoretical sense. But I think we're a little bit in the Wild West right now in terms of trying to understand what's the best way around this. And so we should be open to a lot of the different approaches that could be tried. I do think we need more systematic, careful studies to really understand what ML models are learning from the data, and really try, if it's possible, try this with wide ranges of data, wide model sizes, and so on. Really do a very thorough study to try to understand better what's actually going on, as well as just not really trying to use ML models as a hammer that's looking for a nail. So just because we like one type of model, we should be careful not to just try to use that for every single application area and to try to mold it to make it work, because maybe there are other modeling choices we should also be comparing to and thinking about. And finally, I think another thing that could be worth thinking about as a whole for the community is efforts to go beyond the modeling itself. So how do we actually think about ways to extract knowledge from these models and use that downstream, or use the powerful representations downstream for various tasks? So I'll go ahead and end on that note, and happy to take any questions.
Thank you so much, Aditi, for the great talk. Any questions from the audience? In-person audience? Oh, sorry.
Thank you for your talk, and I really appreciate that you mentioned your study on equivariance versus the transformer backbone. And I also see similar patterns in the past development. Like, I remember in AlphaFold 2, they emphasize on the SE3 equivariance, but in the third version, they just rely on the DDPM for the generation. So I think this pattern might, like you said, if we have more data to train a better model, the model can learn the equivariance itself. Like you mentioned, the 99% cosine similarity, it learns the equivariance, right? But the question is, in some of the applications, like AI for health domain, there's one possibility that we just don't have enough data. So in limited data sets, do you think equivariance will still play a critical role than unified some big foundation model?
Yeah, thanks for the question. Those are all really great points. Yeah, like AlphaFold 3 did remove explicit rotational equivariance from AlphaFold 2. I do think both that and the case studies I talked about were really like, to get to the end point, we had to do some soul searching along the way, which did go through graphs and variance. In cases or fields where there's very little data, the one thing I would say about that is it feels like very few fields are totally isolated, in that if you start out with some large scale model, could you then adapt it in some way to regimes that you have less data? And this is something you can see with even atomistic problems. There's some places where we have very little data, but you can still start with a large model and adapt it in that way. So I think that would be an open question to think about. Historically, these methods with a lot of inductive biases have worked more in small data regimes. But I think the thing that we should be comparing it to now is starting with large models that are fine-tuned or adapted in some way to small data versus just training from scratch on small data. I think there's lots of good systematic studies that could be done there as well.
Thank you.
Any other questions from the...
Yeah, thanks for the nice talk. So my first question is, I didn't understand exactly what you meant by learning the equivariance. If it means like you're memorizing what happens at a certain configuration, or if there's some generalization so that you can predict something that you have never seen before. And then the second question is, I wonder if like the kind of evaluation that you're using that's based on average error can really say kind of what's happening, because there might be some exceptional cases that happens rarely but could be very like impactful with some applications. And so if there are like maybe better ways to evaluate the mistakes of the model.
Thanks. So the first question was, how are you evaluating how equivariance is learned from the data? So this was done based on a held out test set, so something that the models have never seen. And the idea is that you explicitly check the explicit definition of rotational equivariance. So if you predict something and then rotate it, you get the same answer as if you rotate it and then predict it. And so this is done checking, can this actually learn some type of equivariance on something that is considered to be out of distribution, essentially the test set of the system that the model didn't see during training. So that is one example where it was checking not on things that it had seen, but actually on things that it hadn't seen before. And at least that underlying pattern of rotational equivariance did seem like it was learned from the data. To the second point of how you're evaluating the models, was that the question?
Yeah, like just in terms of like whether average error or like accuracy is a good metric for like whether you're actually generalizing like physics properties.
Yeah, I think so. That equivariance test is very fundamental, because it's very fundamentally checking did you actually learn the symmetry of this system? But there have been other studies that have been done, like people have taken these models and tried to actually run molecular dynamics with them, including models that tried to learn equivariance from the data rather than build it in. And in some of those cases, it does seem like things are generally fine. Like the model doesn't blow up, it seems to have learned something well from the data, and it's giving you actual reasonable, stable answers. I do think we need more evaluations and more checks to really understand this, and perhaps it could be different depending on the application area, but some of those checks have started to be done in the community, and it does seem like they are checking out in various ways.
Thank you. And
So thanks a lot for the great talk. I really liked it. So do you think this only holds for continuous group actions like rotations, or does it also hold for, I don't know, permutations or something like this?
Yeah, that's a really good question, and I do think that this is where it would be nice to have more studies looking at each type of group, maybe understanding the different symmetries in the data. I think permutation equivariance was something that I thought was harder to learn from the data than rotational equivariance, but we did, in the process of some of these studies, find that this was also something that you could learn reasonably well with just a fairly large data set. I think it is a harder symmetry to learn, and some symmetries will be easier or harder, so it would be cool to do more studies on that as well.
Thanks a lot.
Hi, thanks for the great talk. Do you think that the fact that a lot of these models are learning the equivariance when they're free to do so, is that maybe a sign that, you know, SE3 equivariance is an important inductive bias, but the way that we're encoding it is maybe not the best way to do so, or that Atom is not the best way to train a model that's meant to be SE3 equivariant, rather than evidence that going fully unstructured is the right way to go?
Yeah, that's a great question and a good point. And in our second study there, we tested a couple of things because we tested equivariance and learning it from the data, and we also tested no graph priors. So what happens if you remove the graph structure? I think the second one is actually a little bit less natural for molecules because molecules don't naturally form to a graph structure, whereas equivariance is something fundamental to molecules and so is something that you know exists. I think it could be a question of, can we make equivariance approaches way faster, way better, and then that would solve our issue. The challenge with that is that there is a great group of people working on trying to make equivariance faster, optimize it, but you're competing against the very large group of people trying to do this with unconstrained transformers and the amount of hardware and funding that's being put into that. So I do think that perhaps if there was a way to make it one-to-one even, it could make sense, but it seems very hard to do that right now, especially if it is easier to learn from the data.
yeah, we do have 3 questions in the Slack channel, but let's prioritize in person.
I was just curious if you could explain the representation. You said for the transformer input, it was Cartesian coordinates.
That's right, yeah. So molecules are represented as XYZ coordinates, like their position plus the atom type. And then that's connected to, say, in this particular data set, it maps to some energy or the forces on each atom. And so the XYZ coordinates plus the atom type of the molecule, that was fed in directly to the transformer as like a token.
Cool, thanks. What about the ordering of the tokens? Does that make sense?
Like which ordering that you put the tokens in?
Yeah.
Yeah, in this case, I don't think it makes a difference because molecules don't have a natural ordering. There's no, if you have like 20 atoms in a molecule, there's no actual order of it's like 1, 2, 3, 4, or so on, or 4, 3, 2, 1. So it didn't really matter in this case.
Okay, so it's sort of equivalent to have like every sort of permutation of one molecule is valid input, basically.
Exactly, yeah.
Okay.
Any other?
Thanks for the great talk. It's cool that you showed that it works quite well with the equivariance formulation. There are some problems where it's sub-equivariance. For example, um, if you think about physical systems, and there's the gravity direction, which is, always acting irrespective of the forces acting in other dimensions. So would this generic framework also account for sub-equivariance formulations? What are your thoughts?
Yeah, so in this case, you mean that within some group you also have sub aspects within that or subgroups within that? I think that would be interesting to study for sure. I know in high energy physics there was some work, I think, on like a point edge transformer that was trying to do something similar of we have all of this data that's been collected. Can we just learn a general model from that data? It would be a good place to explore because my understanding is that that field has a lot of data through many, many experimental measurements, even though it's a bit noisy. I don't have immediate intuition on how it would work if you tried a similar approach over there, but I think it would be interesting to try. And I think given the amount of data, probably the prior is on the side of this might be possible to learn from the data.
Hi, thank you so much for the talk. I was wondering if you could expound a bit more on settings, research questions where structural constraints might indeed show significant improvements, because one concern is that existing metrics or benchmarks might be limited in their diversity or difficulties such that you don't see meaningful differences.
Yeah, that's a great question. So I think most types of problem settings have some type of structure to them. And we saw this with the history of language, for example. Like you had models that put really complex grammar rules into it to really understand, because language is very complex. We saw this with vision. We had models that really tried to encode things about images. And so I think every field does have these structural constraints. It's just that we're seeing this paradigm of some of these structural constraints might be better learned from the data. And part of that might be that there's so much that we don't necessarily know. And by imposing structural constraints, we might be limiting our ability to learn that additional information versus trying to just learn it all from the data. I think you definitely bring up a good point, though, that we need to think really carefully about the evaluations that we're doing and really try to do these systematic studies to understand better. In some cases, do we need to be unstructured? In some cases, can we learn that structure from the data? I have come to feel also that structure is in many ways might be best represented in the data itself, like have very diverse structure in the data and let the model learn and figure out what that looks like.
So we have come to the end of the keynote speaking session. So we have some very good questions in our Slack channel. So would you mind offline replying to them? Like
sure.
some brief answers to their questions.
Yeah, I can go take a look at that as well.
Thank
And
you so much.
thanks for being a very open-minded audience as well.
Yes, and yeah.
Okay, thank you everyone for attending our morning session. So now I'm going on stage to show you something that you can actually collect from the registration desk. So we do have 3 vouchers for lunches, which will be over there. There's the Verdi dining hall that is a buffet, so you can choose whatever you like. There are a lot of different things. And tonight we will have our reception dinner where food will be served outside, and we can either sit in the garden or inside or upstairs. That's for tonight. And you can also collect your t-shirt. So I have collected all your t-shirt sizes. I hope you will like my design. This color is called maroon. It is a special color for ASU. Maroon and gold is the 2 colors that make up of our ASU logo. And you will also have our name card. So whenever you collect a name card, a t-shirt, and these cards, please have a tick on the sign-up sheet. Apologies, it's too small because I made it without optimizing, sorry. I hope you have enjoyed the conference, and we will have the poster sessions in an hour over there. And if you do not have pins with yourself, you can get the pins also from the registration desk. Thank you. See you in an hour, and we can sit wherever we want in the cafeteria, and then we can